last week, we talked about this area around the calcrine, okay? That's the primary visual cortex, or V1. Today you can see that when this light flashes over here, which is below where the person is looking, it lights up, yes, V1 above the calcrine, but then it lights up two other areas above the calcrine. And we'll talk about those areas. And those areas are called V2 and V3. So V1 here around the calcrine, V2 and V3 above it, and similarly below it. This is looking at the medial side of the brain, and we'll rotate the brain so you can see it turn, because here's the back end of the brain, there's the calcrine. You can see that it's a deep valley, and then around it is V2, and around that is V3. And if we rotate it some more, we can see the lateral side, the outside of the brain, and you can see that you can hardly see, we'll back it up a bit, you can see a little teeny bit of V1, and then around that V2 and around that V3. So, this is it unfolding again, and we can see V1, V2, V3, and this line rotating. And you can see that it's not just one line rotating, but you see there's similar lines rotating through V2 and V3. And they do funny things. You can see that over here they're coming together, V1, V2. And you can see at the same time they're separating here at V3 and V2. Okay, so the lines separating and lines coming together. What's that all about? Well, let's take a look at a line that's almost horizontal, okay? So this line, you can see here at the very bottom of the calcrine, okay? And that's where you'd expect the horizontal line, at the bottom of the calcrine. But you can see that there's another line here at near the V2, V3 border, and similarly there's a line in V3 here near the V2 border. When we look at a near vertical line, you've got a different pattern. This line here that was in the calcrine has moved to the V2 border. This line here, was at the V3 border, has moved down to the V2 border. And this line that was at the V2 border has now moved to the edge of the V3. So, what's all this complicated thing? What is going on here? Well, one good thing about that is if you're doing fMRI and want to figure out where the borders are of V1, V2, V3, what you do is you show subjects horizontal lines and vertical lines, and you can determine where these borders are, these dotted lines, where these two lines come together, tell you where these borders lie. And that's what experimenters use to determine where these areas are in living subjects. Now, what's the story behind this? Okay, so you can see here, instead of a line going across like that, we have a line starting from the horizontal and going to the vertical. The point that's at the horizontal is a circle. The point that's at the vertical is this arrow. So let's follow it over here. you can see that the one that was at the horizontal, the dot, is down at the calcrine, and then goes up to the edge of V2. Here, what happens is that the line is mirrored. Okay, its mirror image appears. Okay, so the arrow here and the arrow here. And over here, we see a tail, and again another mirror image. A tail here and a tail here. So what's happening here is cells that are similar to each other are trying to be close to each other. So if you had lots of arrows all drawn here, all those arrows would end here and similarly be at the other side of the border. Similarly, at the tails here would be all together at this side of the borders. So all similar cells are close together, and that reduces the wiring. The other thing that it does is it allows for shortening of the axon. One reason for these folds appearing in your cortex, one theory for the reason that your cortex is all folded, is to reduce the length of the wiring. So you can imagine that there's a neuron here that's representing the tail here. It connects to a neuron here that's representing the tail here. And this axon pulls these two edges together. Similarly, this pulls here, and in that way, you reduce the length of all the axons by having that fold at that position. Okay, so what do these various areas do? Well, they're trying to put things together. We saw in area V1 that we add things like lines and complex cells like lines of a certain length and lines ending in their visual fields. And in these higher areas, they're trying to figure out what are the lines and what belongs together. Like these 4 lines might describe a box. And when the brain decides that, when it's looking at it, you can see these 4 cells. It's undecided which belongs to which. So they are all firing asynchronously at different times. But at some point, a decision is made that these 4 lines belong together. So this is a higher area, either V2 or V3 makes that decision. And the signal then, all these areas are reciprocally connected. So V1 goes to V2, V2 goes back to V1. And so the cells that these higher areas decide belong to the same object start firing synchronously, that is, at the same time. And the one cell that doesn't belong together is firing at a different time. And again, when cells fire together, they connect together, and they enhance each other's activity. So what the brain is trying to do is figure out what's the objects and what's the background. So you look around this room and you can see people sitting there, their faces against backgrounds, and the brain is trying to decide which is which. So over here, what is this, Well, if you look carefully, you might see something, you might see that maybe this is a head of something, and this is another head, and maybe this is a body of something, and maybe this is another body. Can't quite tell, but you can tell now, okay? Because color is a distinguishing feature, and the brain uses all kinds of cues to decide that things belong together and they become objects. So this is what these areas are trying to do: figure out what parts, what lines, what end of lines belong together, either because of some cue, such as color, or some other cue. Now you can notice here that memory is an important thing. You can remember where these giraffes are, okay? And then that memory allows you to keep the little blobs that belong to the giraffe away from the blobs that belong to the background. Now watch this. There's other cues that are important. You can see these squares on each circle rotating, but at some moment the squares become at a certain position, like now, okay, and you can see not like these little edges. You start saying now that this might be a square that's bluish. Okay, it all belongs together. So the cell's looking for connectivity, and they can connect this space here. So a little cell here says, okay, a line ends here and a line ends here. Maybe they belong to the same object. The other thing is that if you look carefully, you might see that this has a bluish tinge to it too. Like where the brain is making this whole thing, this square here, has a bluish tinge where it's white, actually white, So the brain is filling in the color for you. And it's doing that from the edges that it sees over here. So it's, again, making things up. So the process is, you see, there is a visual image. V1 sees it, sends it up to higher areas, and they start interpreting it. And that interpretation might be modified by memory. We saw that when we saw those giraffes, they were easier to see again because of the memory of seeing those giraffes. And that information can modify what's happening in these early areas. Here's another example how the brain can work. You can read this. Try reading it, what it says. And it explains what's happening, if you can read it. So often all you need to do is see the first and last letter, and the brain will make up what's in between, because of all your practice and reading. Okay. We saw V1 goes to V2 and V2 goes to V3. What happens after that? Well, the brain goes to about 36 and counting areas. Every year there's 3 or 4 more areas found, okay? So, and this will probably continue for a long time, I suspect. And these areas go along 2 pathways, something called the what pathway that goes underneath the cortex to the inferior temporal lobe, another one that goes over the top of the cortex to the parietal lobe. And you can think of all these 36 visual areas as going to the Silver City here in Masonville or someplace like that. And you see 36 theaters, and they're all playing movies. The difference is, in your brain, they're playing the same movie. 36 or more different screens. You have 36. Imagine it in your brain. You've got 36 little screens. But what's different about them, they're showing, each screen is showing a different aspect of what you see. Okay? Some are concentrating on the colors. Some are concentrating on movement. Some are concentrating on where the edges of things are. There's 36 of these areas. We know what some of them do, but we don't know what all of them do. Okay, I mentioned that one path goes up and another path goes down. The one that goes over the top is called, the thing that's called is the dorsal stream, besides the wear stream. And the reason it's called the wear stream is that up here, what you're trying to do is direct actions at objects. And to direct actions at objects, you got to worry about where those objects are. So if I want to reach for my mouse, I have to worry about where that mouse is. The stream that heads underneath is called the ventral stream because it goes underneath. And because it's interested in what things are, what it is that you're seeing, who it is that you're seeing. There's the face. Whose face is it? And we're going to look at the wear stream in lecture 6, I believe. And so for the rest of this lesson, we'll concentrate on the what stream, the thing that goes underneath. So you can see that we saw that in V1 you extract simple features like lines. In the inferior temporal lobe, you combine these features for different things, such as defining a particular face. So this process is complex, and it's complicated by the fact, for example, that in V1 we have objects, but then the top and bottom of the objects bottom and top of the objects get separated into different areas. V2, the top, the bottom in here, the top here. So there's a spot here called the lateral occipital complex, and it puts together things that are on the same side. So this one on the right side is interested in what's on your left visual field. And it doesn't put together the right and left, it puts the top and bottom together. So we saw that we have these spokes and these blobs in V1. And over in LOC, through V2, V3, and several other areas, we start putting together that maybe these little edges here belong to an object. And at least the top and bottom of the object is calculated here, and its opposite side is calculated on the LOC on the other side of the brain, the left side of the brain. And finally, we get to the inferior temporal cortex, where the object is recognized. And for example, in an area called the fusiform face area, faces are recognized. So the left and right side of the face is put together, and you recognize who the person is. If you don't have LOC, you can't recognize objects, any object. The face, like your can of Coke, your mouse. You can tell that this object here, you can't tell it's a mouse, but that it looks metallic and it looks white, but you can't tell what it is. And that's called visual agnosia. Now, lesions in IT then start causing loss of particular objects, not just all objects, but particular objects. Like you can have an area that causes you inability to recognize rhinoceroses. So, in a famous what's the evidence for these dorsal and ventral streams? So this lady called Ungulator and this man called Axby asked subject two questions. The first question they asked is the same face as you just saw. Is that repeated? So press the button when you see a face repeated. Doesn't matter where it is. So we'll do that now. Again, we use our hands as clickers, and hit your hands as hard as you can when you think a face is repeated. Correct. Okay. So while you were doing that, okay, all your attention was focused on the memory of that face compared to the next face. And areas underneath your brain were being activated. So that's what Ungulator and Axby saw. They then asked, with exactly the same stimulus, a completely different question. Okay, is the face that you just saw in the same location as the previous face? Okay, so we'll try that again. So again, you're not looking for the same face, you're looking for the location being repeated twice. Good. So while you were doing that, okay, exactly the same you're seeing exactly the same thing, but a completely different part of the brain is being activated, because you're not looking at what the face looks like. You're looking at a location. Okay, so same stimulus, different part of the brain gets becoming active. So you can see here too another thing what's happening with the brain. When the questions change, different parts become active. Okay? So oxygen is being sent to this part of the brain for this problem, another part of the brain for another problem. Making sure you optimize the flow of oxygen. So, again, if you have a lesion of this area, as you might expect, a person will have difficulty pointing or grasping accurately. If you have a lesion of this part of the brain, for example, LOC, you'll have difficulties finding the mouse from a whole bunch of other objects, and other problems with other areas. Nancy Canwisher, about 15 years ago now, found that there's a small region underneath the brain here that's responsible for faces. It lights up when you're doing something to do with faces, like deciding whether this face is someone you know or someone you don't know. And there are other regions that light up for different types of objects. And here you find, in FFA, you have clusters of cells that light up for particular faces. So, very selective neurons for a particular face. Now, when people have lesions here, they have something called prosopagnosia. Remember, before we had agnosia, that's an inability to recognize anything, any kind of object. Now we have prosopagnosia, which means we can't recognize faces. I'm not sure why they come up with such difficult names for things, like have a face agnosia. That's much simpler to remember, but anyways. If you have this problem, you can't even recognize yourself in a mirror. Okay, and when you get home, you should look at one of the links, and you'll see that they do a test on someone who happens to be a photographer, taking pictures of people, and he can't recognize faces. And they test him. Two ladies appear in front of him. Okay, you've seen them both. They go away. They come back 5 minutes later, and he can't tell which one is which. But the patients that have this problem can recognize faces from other modalities, such as their voices. They can also recognize colors, and the color of the face, the color of the hair, lips, and everything like that. So just imagine one of you is out with someone, your mother or your boyfriend, girlfriend, and you're in Loblaws, and you separate and then meet at the, say, okay, we'll meet at the checkout counter. You're looking at the sea of faces, and if you have prosopagnosia, you won't be able to pick out who it is that's the person you're looking for. It's an amazing thing to think about. Okay, so in the inferior temporal cortex, including FFA, you have cells that are looking for particular things. So this cell doesn't like rhinoceroses, likes lions, doesn't like giraffes. So it's a cell that recognizes this type of object. And it can tell it's this type of object no matter where it appears in the visual field, whether left or right, up, down. It doesn't care because these cells have huge receptive fields that cover both sides. We saw, and this is important, we saw that in V1 you just have the contralateral visual field, okay? But here the two sides come together and you can see the whole thing. And the size doesn't matter, so you can recognize this object as a lion no matter what size you have. You can also, it doesn't matter how it's defined. You can recognize the lion here if it's by its lines, by its color, by its texture. And you could recognize these lions by connecting the lines that are moving, okay? You pick out the moving lines from those that are not, and you can see the lion. Watch when those lines stop, okay? When those lines stop at the edges, I don't stop them for long enough, the lion disappears. See quickly how it's gone? And then you can, when it starts moving, you pick them out again. So movement is something that allows you to pick out what's the lion, what's lines that are identical from each other, but by this cue. So the other interesting thing is that in IT, objects that are very different, like this is a rhinoceros and this is a lion, and so he can tell the difference between the two. But if you look over here, V1 would light up for this edge, and V1 for light up for this edge. Okay, it like doesn't care if it's a lion or a rhinoceros. And over here, you can see that they might look very different because of different sizes, but you can still tell both are lions. Okay, but they light up a very different part of V1. Here they light up the whole of V1. Here they light up this tiny little part of V1. But in both cases, the inferior temporal lobe determines it's a lion. So it's a striking ability. All these pictures will cause you to see Obama getting younger and younger. Okay? And it could rapidly recognize that it's Obama in about 100 milliseconds. Okay? So it's a really fast system. You can imagine there's thousands and thousands of faces that you've memorized over the years. And you can pick out which one is which in about 100 milliseconds. So it's a really fast process. And you can think of that as meaning, because this picture, or this whole series of pictures, means, oh, this little button is not working. I'll have to fix it. All those different pictures meant the same thing to you. Now, cells within this inferior temporal cortex, like everywhere else almost in the cortex, are made up of columns, okay? And neighboring columns represent similar things. Lines that have faces from different views, or letters that look somewhat similar. One thing that's interesting is that if you look when you look at a picture, for example, you point your fovea at different parts of the picture. And when you look at a person from close up, you look at your fovea over here, over here, over here. And so what the brain is seeing is just little snapshots of different parts of the face. And yet by these different snapshots, you can put together the whole face. This is my daughter many, many, many years ago. I'd say about 39 years ago. Okay, here's another problem, okay? You can see these two lines here, two yellow lines. I want you to bang on the table. I'm going to reduce the length of this line in closest to you, and you tell me when the two lines become equal. I think I'll reduce it. Oops. And then there's something else to fix. Well, if it had worked, you would find that when the two lines were about this length, you would think they would be the same, but you can see the illusion that of how much you'd have to reduce it until they were actually the same. So this picture here of this window is being distorted. And it's being distorted by this Watt pathway. And it's being distorted because we recognize the parts of the picture as the objects they are. We know that a window is rectangular. Okay? And knowing that it's rectangular causes a distortion. And in order to play things or draw things as they really are, you have to get rid of that distortion. So that's why drawing takes practice. What you see is not what is there. Your hand has to draw this undistorted image. So you have to learn to point your pencil not where you think you see it, but where it really is, okay, due to that distortion. That's why drawing isn't something that you can do. You can't reproduce this picture right away. You'll get the perspective wrong the first time. But with practice, you can draw pictures with the proper perspective. In history of art, you notice that the old ancient pictures are all up here flat, and only suddenly did people discover the process of drawing things with depth in them. The other thing that's odd is that depending on how the face is like when it's upside down, you can't tell there's anything wrong with Mona Lisa. But when she's right side up, you can tell that the eyes and the lips are wrong. Why is that? Well, when we've seen a lot of Mona Lisa, we can remember her somewhere in our brain. We have a picture of what Mona Lisa should look like we have a picture of everyone else we know. And that picture is sort of stored in a certain frame of reference, in a frame that we usually see that person. Usually see that person as upright. And so when you compare what you're seeing now to what you remember seeing, it's easy to compare the lips that you see now to the lips that you have stored in your memory. But when you compare an upside down face, you have to rotate those features to compare them to what you saw before, and that's difficult. And it's difficult because probably we haven't practiced that rotation. Okay, so in summary then, V1 divides into two streams, an action stream or aware stream that is concerned with the spatial relationship between objects. Okay? And what is possibly not appreciated at once is that it's largely unconscious. I can reach for this mouse while I'm talking to you. I've been reaching for it all this hour, and largely I've done it unconsciously, as you do for your mouse. In contrast, the what stream, you're conscious of who it is that you're looking at, the objects. So consciousness is an integral part of the what stream, and you use that for recognition and perception. The what stream is different because its information comes primarily from these small cells in the fovea. Remember the visual grasp reflex. You see something off on the edge, and then you point your fovea to it, and then you can tell what that thing in your periphery is. In contrast, the action stream gets most of its information from things off to the side. When I reach for my mouse, I can see it from the side of my eye. Okay? And so if I don't know where it is, I can usually direct my movement to it without looking at it, because I can see it by these ganglion cells that are in my peripheral retina. So in lesson 5, we'll see that these two sides aren't equal in their properties. The left side represents mostly things like language, recognitions of words and sentences. We'll discover that there's an area similar to the fusiform face area, but one for recognizing words. Okay? It's in the same place in the fusiform face area, but it's been taken over by the recognition of letters and words. The right side, it does tasks that mostly the recognition of objects. So the picture of the face is usually represented on the right side. The name of the person is usually represented on the left. That's perhaps why it's sometimes difficult to remember. You remember the face, but you can't remember the name. You have to have this connection wired properly. Okay, that's it. Thank you very much.